Hello and welcome. Um, in this presentation, we're going to look at topic 11, and we're going to look at unknown input observer designs for time delay system, which we considered earlier in chapter 5 in our book. Now, in that particular chapter, when we did the decomposition of the unknown input, and where we try to express the unknown input in its entirety, we impose the following constraint on the matrix CD. And so that was the development in there. And when we impose the constraint on the matrix CD, which is this constraint, we have two conditions. One is V1 times CD is 0. The other one is the rho associated with the output measurement Yi of t. That matrix CD, the rho in there, had to be the left node space of D. And in that situation, we have two radio order time delay systems with disturbance free, which is this one, and the unknown input is expressed in terms of generalized functional. For the case where this constraint is satisfied, it's a bit more relaxed. However, we have a time delay system with multiple time delays, as well as the unknown input include generalized functionals. So in that discussion, this is the assumption that we impose on the matrix CD. We're going to revisit chapter 5, and then we're going to look at another approach for design unknown input observer for this time delay system. And we call it an expanded dimensional approach. And so how did we come up with that name? The reason for that is we can introduce a stack vector, which is the delay stack vector, xt minus tau. And if we have this introduce this vector, then we can actually augment that together with the original vector, and that's the development in this chapter. Okay, so let's have a look at how we went with the development. So we introduce this delay stack vector, and then when we have this delay stack vector, we take the differentiation of it, and then we substitute this expression in. So that where this time delay system, this equation, and this equation, we obtain two equations. So the first one is we replace xt minus tau by this delay stack vector. And then the second equation is we take the differentiation of it. And so we obtained this equation. Now, bear in mind that in this equation, we have the unknown dt minus tau in there because it's actually been delayed by tau. And so we have this equation. So we got two equations together. And so we define a new augmented stack vector. We call it x bar xit, consists of two stack vectors. One is x of t, and the other one is xt minus tau, which we call with this name here. And so similarly, we can also call a new unknown input vector. It's no longer one unknown input, but it actually has two in there. So we call it a vector. It has d of t and dt minus tau, which is the one in here. As well as we call this augmented matrix, which basically comprising of I, ID, and a 0. We see this matrix here. And this new delay matrix we call IDA. So the notation is that DIA stand for the augmented um, matrix. So we have D1 and D2. So this unknown input matrix consists of D1 and D2, where D1 is this basically that column there. In here, um, this system itself has only one unknown input. But when we introduce this delay stack vector, and when we stack them together, we augment them together, we obtain this expanded time delay system, and that's where we call it an expanded time delay system approach. Okay, an expanded dimensional approach. So we augment these two equations together, and we define the augmented factor and all of that. So that's where we got this uh, global, we can call it a big time delay system. Now, the distinct feature about this um, augmented or expanded time delay system is that the output measurement vector itself and now contained in expressed in terms of this augmented stack vector. So what we can see here is that the delay, stack delay xit minus tau actually disappear. However, at the expense that the dimension of the system is twice the dimension of the original time delay system, as well as we have two unknown inputs in here. Okay, so this expanded dimensional time delay system has that particular feature. The output measurement vector now only contains just the stack vector itself. There's no delay term in there. But the other hand, on the other hand, the dimension is bigger, and the number of unknown inputs here is now 2. We have a vector, unknown input vector. So we have the unknown input dt and the delay of it, a delay version of it. So this is another way of looking at the unknown input estimation problem. And so we let us continue on with the analysis. Now we remember in our chapter 5, we impose this structure. We would like to see whether this structural constraint can be relaxed. That's why we investigate this expanded dimensional approach. Okay. So we, as usual, we have this big time delay system. Now, bear in mind that the dimension is twice the previous original time delay system because number of stack variables now become 2n, and there are 2 unknown inputs. So if we want to estimate the unknown input dt in the presence of its delayed unknown input, and as we discussed in our previous chapter where we did the unknown input decomposition, we look at 2 possible approaches. One was that we only use one output, first derivative of one output measurement, and that's what we call design approach 1. Okay, and now what we're going to do is let's investigate 2 approaches. The first one is the design approach 1, where we want to achieve the decoupling of the unknown input dt from the other unknown input. Remember that in this vector here we have 2 unknown inputs, d of t and dt minus tau. And so we want to do the decomposition where we just use first derivative of one output measurement only. And for the sake of simplicity in the presentation, we assume that we're going to pick the first output measurement, which is y1 of t. So from this time delay system, we pick the first one. We pick the first one, and that's what we need to impose is the constraint given in here. Okay, we need C1 times D, which is the first row of matrix C, and this has to be non-zero. And of course, the when we look at metric DI in here, metric DI in here, we can also see that it is of this particular form. So if we have C1 times D is non-zero, we can also ensure that the unknown input, the entry from the t minus tau is 0. So that's where we can actually achieve that decomposition. Okay, so we require this observer matching condition holds, and that's the assumption. And if it holds, then we use the first derivative of this output measurement y1 of t. And so in our decomposition, we choose matrix T according to this structure, where E is now an expanded dimension. Remember that we are dealing with an expanded system with dimension 2n. So we pick matrix E according to this structure. And because C is in canonical form, so that will ensure that metric T is invertible. And D1 is this column in here, that one there. And we can ensure that the first entry of it is non-zero. That's it because we impose the condition, this condition should be satisfied, okay? And similarly, the matrix V is invertible, and we pick the first column of matrix DI. Remember, DI has two columns. And so we got this very standard decomposition from chapter 3, approach 1. And by applying this stack transformation into this stack transformation is the one that we have in here. And we apply it to the big system, which is this one. We can express, we can do a bit of partitioning and all of that, actually explain in the following below here. The bottom line is that when we do the transformation, we apply this stack transformation to this big system, then we obtain the following equations. Have a look at that. Now, the thing about the first equation, 710 in here, is that it has this delay unknown input in there. Just like in our previous chapter 3, when we did the decomposition, we have a reduced order system with an unknown input or with unknown input. Here we have it, but the unknown input in here is the delay version of d of t. And we have another equation here, which is we can explicitly express dt in here. Now, to achieve all the decomposition, we just multiply both sides of equation 712, which is this one here, by V inverse, just like what we did in the previous discussions. so that we can split that into two equations. And that's exactly what we obtain in here. And when we have these two equations, we can see that the output measurement, the reducer, the output measurement vector is basically in terms a combination of this reducer, the stack vector. And this one has a dimension of 2n minus 1. 2n minus 1. And the other equation is in terms of the stack variable x bar I2 of t. Now we can express it in terms of the output measurement y1 of t, because V1 is specific structure. It only has one non-zero element, the first one. So this is y1 of t, and this is in terms of this vector here. And that's exactly what this equation is. And then, of course, we can take the differentiation of it. That's where we have it in here. And bear in mind that when we got this expression, the derivative of the stack vector x bar I1 of t, which is this one in here. So what happening is with that information, we substitute it in. In fact, the disturbance, which is the unknown input d of t here, also contains the delay unknown input. Okay, so that's the main thing in here. So when we look at this equation, this is the results of substituting this equation and together with its derivative back into this equation. And now, so when we do that, when we after completing that task, we obtain, and then also we substitute that back into this expression in here to obtain dt, the unknown input. And when we do that, we have the equation expressed as follow. It's important to note in here that the unknown input is also including this delay unknown input in there. Now, if we want to really asymptotically estimate this unknown input, we must have this term equal to 0. Otherwise, we can't guarantee the error asymptotically goes to 0. So that's the key there. So we then have to say, look, we have to impose a condition on this matrix here. And that means that it boils down to this requirement. Now, when we have this requirement, taking into consideration that the matrix C is in canonical form, matrix V1 is of specific structure which has the first non-zero element in its row matrix, and take into consideration that matrix E of this special form here. So what we can then conclude is that these requirements, in fact, is the same as the requirement that we impose on in chapter 5, which is this requirement in here. It's equivalent to this condition, or these two are basically as a consequence of this one. So interestingly, yeah. So that means that we boil down to the same requirement. In order for us to explicitly obtain this unknown input in its entirety and to ensure asymptotic conversion or estimation of this unknown input, we require this term equal to 0. And if this sum equal to 0 is actually equivalent to either conditions 5.9 or 5.10 in chapter 5. So in chapter 5, when we did the decomposition, we actually arrived at this requirement. Now, this requirement is also required. This is also required in this approach here. This is approach one. Remember that. This approach one, we say that when we do the decomposition to express the unknown input, d of t, using only first derivative of the first output measurement, then we apply these matrices transformation and this metric V. And so we have to then impose the requirement that this has to be 0. Now, this has to be 0 means that either this condition hold true. If this condition hold true, is the same as condition 5.9 in chapter 5. Or if this one is a condition hold true, we require V1 CD time D equal to 0. And so if this is satisfied, then of course we can then have this is much similar expression because we got V1 CIE equal to 0, which is this bit here. There you go. If that one is 0, we only have that. And since we have that, we don't have that derivative in there, and therefore we can overcome the delay unknown input in the expression, for the unknown input. And that's exactly where we get the reduced order time delay system with an unknown input, in there. And that unknown input is the delay of the unknown input, dt minus tau. And this unknown input itself is in terms of the first derivative of output measurement y1 of t itself, and also a linear combination of a stack vector. And that's where we say, look, to estimate this unknown input, we will need to design a functional observer to estimate this functional directly for a time delay system with an unknown input. Okay, with an unknown input. The other bit is where we compare this one with the one that we obtained in chapter 5. This system itself has a dimension bigger. It has dimension of 2n minus 1. All right. Instead of n minus 1. And it also has an unknown input in there as well. Okay. So that bear of that in mind. And then when the other requirements, like the other conditions, other condition is equivalent to this one. So in other words, if we then say we need to have this term equal to 0, doesn't mean that V1 CIE is 0. It's basically the left node space of D bar 2. We then have another time delay system with an unknown input, which is this one in here. Okay, which is this one in here. And then there's still an unknown input, which is the delay unknown input. And the functional is now a generalized functional, which is a combination of this vector and its delay stack vector. So we then had to design a generalized functional observer to asymptotically estimate this in order to realize the unknown input asymptotically. So when we look at approach 1, where we say we're going to do the decomposition for this big expanded dimension time delay system, we still require the condition imposed in chapter 5. But we arrive at a time delay system, a reduced order system with a higher dimension. and it has an unknown input in there. So it seems like this is not a very good approach, isn't it? Because it's actually resulting in a higher review order time delay system compared to the ones in the chapter 5. And because of the unknown input, presence of the unknown input in the time delay system, that also cause more conservative conditions, and that's exactly what we found uh, during our investigation of this approach. And so to be able to design generalized functional for this time delay system with an unknown input in there, we develop some results on that. We obtain some assistant conditions, and one of the conditions is the unknown input decoupling. So that impose another constraint onto the design of the observer. And that where we can see the drawback. The expanded dimensional approach leads to conservative observer design conditions for the case where we want to design a generalized functional observer for this time delay system with an unknown input. And also the dimension is higher. Okay, the dimension is higher. It's 2n minus 1. And we had to deal with the requirement that the unknown input here must be decoupled when we design the unknown input observer for it. So that's where the constraints, the conservativeness of this approach, and we can demonstrate that in an example where we took exactly the same example in chapter 5. In chapter 5, we could design a first order observer. But when we do this expanded dimensional approach, and when we design a functional to estimate this functional of a time delay system with an unknown input, the conditions will not satisfy. And so that where we say, look, that reaffirm, that highlights the attractiveness of the approach we use in chapter 5. So now you might be wondering now why do we investigate this expanded dimensional approach where we can see the conservativeness of the results compared to chapter 5. So what the purpose here? Of course, the first purpose is to highlight the approach that we undertook in chapter 5. And then we're going to see, look, there's still something useful about this expanded dimensional approach. Okay, and that's where we can overcome the structural constraint. So we basically would then say, all right, when we did it in our chapter 5, or when we use this design approach 1 in here, when we express the non-input in its entirety, we find this issue in here. So we have to impose this constraint. And this is based on the requirement that we only use first derivative of only one output measurement. Now, have a look at this bit in here. Now, another way that we can do is we can then estimate the entire non-input factor in one go, which means which contain two unknown inputs. Now, if we do that in one go, then therefore there won't be any requirement on this constraint in here. Okay, so that's where we can see an advantage of using this expanded dimensional approach to investigate the non-input estimation problem. So that's where we discuss this design approach 2 in here. All right. So we want specifically to overcome these constraints. And in this constraint, that means that it's equivalent to this constraint there. We don't want it to be satisfied. What happens if it doesn't satisfy? That means that we don't impose any constraint on the matrix CD. All right. So then let's reconsider the expanded time delay system. The expanded time delay system is the one that after we introduce the delay stack vector, we obtain this expanded dimension of the time delay system there. So let's have a look at that, and let's undertake the second approach. The second approach is, okay, we going to look at this system, and then we're going to look at decomposition. Okay, a decomposition, and we're going to say, look, we make an assumption now. We're going to use first derivative of two output measurements to overcome this requirement. That means that we don't impose any structural constraint on matrix CD. Then the price that we had to pay for, is that instead of only first derivative of only one output measurement, we had to use first derivative of two output measurements. Okay. So in that case, we then assume that Ci times di has to satisfy the matching condition, observer matching condition. Okay, and that's this one is here. And of course, the number of output measurements had to be bigger than 2 in order for us to obtain a reduced order time delay system without unknown input. And the output measurement of the reduced output measurement vector is available. So P has to be bigger than 2. All right. So this is where the requirement is. This is the trade-off. Everything that we do seems logical, because if you want to overcome something, we had to pay for something. And that's exactly what's happening here. So now we have to use first derivative of two output, and let's call them y1, y2. And so that means that y1, y2, the first two output matrices, this condition must be satisfied. Okay. And if that's the case, then we're going to rearrange the output measurement vector. Remember, the output measurement vector cell is basically a linear combination of this augmented vector. And so what we have in then is stack the first two output measurements here, and we call CA1, which is basically a row metric of dimension 2. And that where it has to multiply by DA. It has to be of rank 2. Okay. Matching condition. And so once we done it, we then follow the same process. We pick the metric V according to this form, where DI is the big unknown input metric, DI associated with the vector here. Okay. And P is of specific structure, so that we only need to use two output measurements, and we only take the first derivative of those two output measurements. And that's where we got this metric V1 like this. And then we can also obtain the transformation metric T according to this structure. Now, DI is now we take the whole metric DI in this approach. Before, we only took the first column. Now we take the whole metric itself when we do the stack transformation. And where E is no space of V1 CA. Okay. And so if we do that stack transformation to this big global system, then we obtain straight away the two matrix, the two equations here. And have a look at this bit here. That entire vector is in itself here. This equation itself does not contain unknown input. And so we can then partition all the submatrices. And then from this equation, we pre-multiply both sides by an inverse of metric V. And therefore, we obtain two equations. In these two equations, the good thing about that is in terms of the two output measurements, Y1 and Y2, because V1 itself is of dimension 2 by P, and it has this block here, we see a 2 by 2 block. Okay. And that's why when we take V1 times Y, we basically having two output measurements. And the dimension of this one is 2. And so we got a reorder system output measurement vector as well. And then we obtain a reorder time delay system, which is disturbance free. And the output measurement cell there. So this is a standard time delay system. And the unknown input itself is a vector now. This vector is expressed in terms of first derivatives of two output measurements. It delay and it instantaneous, those two output measurements, y of t, y1 of t and y2 of t. And this linear combination, this is a generalized functional, okay? And so if we want to only estimate the unknown input, then what we say in here, we just pick the first row of it, the first row of it. And the first row, this one here is a generalized functional containing two functionals. And so if we want to estimate only this unknown input, we just pick the first row of it. And that's where we got this generalized functional, scalar generalized functional. And so we can then design a generalized functional observer, which is for that one, to asymptotically estimate self. And that's where the development of our generalized functional observers in chapter 13 can then be applied. So you can see that based on this expanded dimensional approach, we can overcome the requirements. In other words, we can overcome the requirements imposed in chapter 5 about the metrics CD. But the price that we have to pay for when we employ this expanded dimensional approach is that we need to use first derivatives of two output measurements. To overcome this constraint there, we have to use first derivative of two output measurements. So that's the price to be paid for, and depending on the circumstances, practical realization of it, we can either pick this dimensional approach, or if we have the constraint CD is satisfied, then we don't need to use this expanded dimensional approach. There's no need to employ first derivatives of two output measurements. Okay, so basically we're given the designer more options to go about designing a non-input observer to asymptotically estimate the non-input. And so this is where we pick an example. We take an example. Now, in this particular example, when we look at it, we can see that it's a time delay system with two variables. But because of the time delay presence in the stack vector, so the output measurement vector actually consists of three output measurements, and that is something not very conventional in normal observer design. You can see here that the number of output measurements actually exceed the number of stack variables. The reason for that is even we have three output measurements because they are combination of the instantaneous and the delay stack variables. Even with all this information, uh, three measurements, we still can't explicitly realize X1 or X2 in terms of these three output measurements. You see that? So that means that an observer is still required to estimate whatever linear combination or whatever there of the stack variables or the delay stack variables. The reason for that is when we try to solve for X1, X2 in this situation, we have this case in here. X1 is in terms of all these output measurements, but then we have a sum of X2 and its delay in terms of this. So that means that with this information, we still can't express X2 in terms explicitly in terms of the three output measurement or any delay of that. Okay. So if we have a situation where when we do the decomposition and the generalized functional content in let's say x2 x 2 t minus tau whatever there, then we can't realize the unknown input directly without an observer. Okay. Now, so when we want to, and also notice that the matrix CD here, the matrix CD is cell here, and when we multiply by D, CD times D, you see that V1 CD times D is basically non-zero. Okay, so that means that the assumption in chapter 5 does not hold. And that's why we employ this expanded dimensional approach, and we employ in design approach 2 in this chapter. Okay, so when we stack the original system together with the delay stack vector to form an augmented system of dimension 4, we can carry out the design. Okay, so we got this augmented system. We get this augmented system, which is the one given here, and then we employ the decomposition based on matrix V, matrix T, and all of that to this example, and that's where we got this matrix V here, and when we do the inverse, have a look at this matrix V1 there. As you can see that it has a 2 by 2 block in there. And that implies that when you got V1 times Y of T, the three measurements, it's we require, the first one is like 3Y1 of T minus 1Y2 of T. So we need to take the first derivatives of output measurements Y1 of T and Y2 of T. Okay. Now, the metric T is, this is the metric E itself, which is the generalized null space, the null space of V1 times CA, and this is the unknown metric DI itself. Okay, that one 2 columns, which basically consists of this and then the other one, which which is basically this thing here, 1, 2, 0, 0, and then 0, D, which is done. So with that two columns there, that belong to matrix DI. Okay, so matrix DI. That's where we have this transformation matrix. Okay, and so we obtain a radio order system, which is this one in here. And the output measurement vector is now just one output measurement. Is a combination of y1, y2, and y3. And this matrix C tilde 1 is in this form. So in our observer for the unknown input, you can see that we just pick the first row of it, the first row of B1. That's where we have this. Okay, that one in there. And then this thing in here is the one that we have here. Is a scar generalized functional, and it's actually a combination of these stack variables of the stack vector in here. So it has this term in there and that term in there, which are unmeasurable from this measurement here, because this matrix C1 tilde does not contain the second stack variable in there. So we need to estimate desired generalized functional observer for it. And this generalized functional is for the reduced order time delay system with no unknown input. Okay, see this one here. And so we can then realize a generalized functional observer, which is based on the development in chapter 13. And we got an observer. Okay. This observer itself, all the parameters they are given in here. And that's where we achieve the asymptotic estimation of the unknown input. Bear in mind that in this approach, we need to have first derivatives of two output measurements. Okay, two output measurements. We overcome the constraints imposed in chapter 5. Okay, so as far as the expanded dimensional approach present in this chapter, the usefulness of it is the ability to overcome the constraint imposed in this chapter 5. The price that we had to pay for it is the observer now requires first derivative of two output measurements. Okay, and so that's where we investigated this topic itself, and we call it an expanded dimensional approach. When this expanded dimensional approach, and if we only look for first derivative of one output measurement, which is the desired approach one, it's not a good idea to do it, because we still require the constraint in here. And even with this constraint imposed in here, the observer conditions, which involve the design of functional observers or generalized functional observers for time delay system with an unknown input, is actually more conservative. All right, so there we go. We offer another approach, and we call it an expanded dimensional approach. And so we re-look at this time delay system. And when we try to overcome the constraints imposed on matrix CD. Of course, if those constraints are satisfied, we should use the results in chapter 5 because that gives us the requirement of the first derivative of only one output measurement. Okay, so that's basically the development in this chapter 7. And so when we see you again in the next video, we're going to look at the situation where we're going to design a non-input observer where we look at two time delays. Okay, we look at two time delays in the stacked and output vector. So like, for example, we're going to look at this particular class of time delay system where we have an unknown input. Now we have tau and h, and there are delays in the stack vector, stack equation here, as well as the output measurements also contains the delay tau and h. And what we meant in here is that the two delays, they are non-commensurate. That means that tau here is not a multiple of h, for example. If we have tau, let's say 1 second, and h is 2 seconds, they are not non-commensurate. Okay, so that's what it meant. So the reason why, if they are not commensurate, is that it's actually more difficult to do. Because remember last time when we did the decomposition, we came up with time delay systems where we got a delay tau here and a delay 2 tau here. This is just multiple of that. Whereas in here, those two delays, they are non-commensurate. Okay, so you can see that we undertaking investigative research, expository research to explore a wide range of time delay systems, and then we look at how do we design an asymptotic of unknown input observer. And then, of course, when we deal with this kind of time delay system with non-commensurate delays, the decomposition will result in a fairly complex reduced order time delay system with unknown input, without an unknown input. But then it's going to be very complex in some cases, and that's where we're going to discuss in the next few presentations. Just a headline, for example, when we do the decomposition for some constraints, we also arrive at a reduced order time delay system with multiple delays and mixed delays in there. And so that open a lot of open problems for future investigation. Okay, so thank you very much for watching, and I'll see you again in the next video. So bye bye for now.